Hi, it's time for another math easy solution. Time to discuss further into trigonometric substitution for integrals, and now look at example 7 of the example series and solve this example, which is find the integral of x divided by square root 3 minus 2x minus x squared dx. So in this example, it seems pretty complicated, and it's not straightforward how we could use trig substitution because it doesn't look like the form we're used to. But we could actually change that. Yeah, so if we were to look at this inside function, or this function inside the square root, we could actually manipulate it to use trig substitution. So basically, to use trig substitution, we first need to transform the function to make it into the form that we are used to, like the ones I went over in my earlier videos, by first completing the square of the function inside the square root. So basically, if we look at this, the inside function, 3 minus 2x minus x squared, first what we could do is take this negative out, so this equals 3 minus 2x plus x squared. So again, we're trying to make it look like the forms that we're usually used to. So now if we look at this separately, this one right here, so we have x squared plus 2x, just rewrite it like this. And now if we complete the square, and before I get to that, I'll just show you what I mean. So basically, if we had, let's say, a function looks like this, x plus a squared. Now if we were to expand this out, this would equal to x squared plus, well, this times a twice, so 2ax, put that in front, and then a times itself, so a squared. So as you can see, when you expand this square, we get this. So if we were to write this in the form of this, we would first need to do is add a constant. So let's just add a constant c, and now this equals 2. If this was equal to this, equals x squared plus 2ax plus a squared. So if this is the case, then this 2 right here has to equal this 2a. So 2 equals to 2a. So basically the 2's cancel, a is equal to 1. And now this c is this side, that's a squared, and this x is just x squared. So we get c equals a squared, which equals just to 1. So this equals to 1. So what this means is we could rewrite this whole thing. So this would equal to 3 minus, so 2x x squared equals 2 now, 3 minus, now we have an x squared plus 2x, and now we add this plus 1, and then we subtract by 1 so that we don't change anything. So these add up to 0, so we're not changing anything. So it's still the same function as this left, but now this right here is, we can complete the square. This would equal to, well, just x plus 1 squared, exactly how this is right here, where basically where a is equal to 1, which is exactly what we went over that. So now that we have that, and now if we simplify this further, take this, make this this negative 1 out of there, so we get basically plus 1, because there's a negative of a minus, a plus 1, and then a minus. Now this is just, well, x plus 1 squared. So this equals to, add these up, 4 minus x plus 1 squared. So now we get this right here, which was 3 minus 2x minus x squared equals 2 square root, and I'll write this 4 as a 2 squared minus x plus 1 squared. So this is almost in the form that we're used to, so we let u equals 2x plus 1. So when we do this, then we get basically right here 2 minus, well, u squared. So as you can see, we have this, and then if we plug this all inside, so we get square root x, and this one, we are used to this one, so we know this one from earlier videos, how to use trig substitution, so make sure to watch those videos. So now what we get is right here, this would be 3, actually no, this whole bottom part would be, now, so I'll write this out first, so 2x x squared dx. Now this equals 2, so then this x, that's going to be, well, let's rewrite this, x equals 2, well, u, and then subtract the 1, so minus 1. So we get u minus 1 divided by square root. Now we got this 4, or 2 squared, right here, minus u squared. And now this, we have a dx there. Now the dx, well, we could just take this over here and write, well, du, that's just equal to, well, dx, because the derivative of x is just dx, is just 1, and then derivative of 1 is 0, and writing a differential like that. So this is just du. So now that we have this, now we could apply trig substitution. So what we could apply here, like I showed in my earlier video, especially the introduction one, we write u equals 2, or let u, I'll write let, so let u equals 2 sine theta. And now the reason we do this, actually before I get to that, first we got to get the, we have to draw out where this is defined at. So as you can see, this function looks something like this. And the usual one to make it a one-to-one function is from here to here. So if this is equal to, let's call this sine, I'll just write 2 sine theta, and this is at theta. So then we have from here to here is, so theta is defined from pi over 2 to negative pi over 2. And you can see my earlier video on one-to-one functions and trig substitution to see why it's this. And here we don't have this equal sign, so it's not equals to, because if this was equal to, then we get the scenario here where sine, for example, sine pi over 2 is equal to 1. So sine pi over 2 is equal to 1. So then multiplied by 2, that would get 2, and then 2 squared will have a 4 minus 2 squared equals to 0. And we get this scenario where we're dividing by 0. So it's not defined. So we can't have that. So we can't have it equal to any of these points, or negative 1 here. So now that we have this part, let's just get du first. So du is equal to the derivative of this, 2 cosine theta, and then always add the d theta there. So now that we have that, so now let's simplify this function right here. So this is 2 squared, or 4, minus u squared, which equals 2. Plug in the u, which is, well, 2 squared sine squared theta. So we plug in u equals 2 sine theta. Plug that in, and what we get now is, and take the 2 squared out. So we take this out, so we get 1 minus sine squared theta. Now this equals 2 square root of 2 squared, that's just 2. And now this, we know the trig identity, this equals 2 cosine squared. So what we get now is cosine squared theta. And now this equals 2, and then absolute value of cosine theta. And the reason it's absolute value, like always, is that this square root function is positive. So anything inside it has to be positive, and overall has to be positive, because it's only defined when it's positive. You can't have a negative square root based on any numbers inside. So anything inside needs to be positive. So, but we know that when we look at the graph of, well, cosine theta, this is theta, this is, let's go y. So we know it looks something like this. So it keeps going on. And at this point right here, this is pi over 2, and this is negative pi over 2. So that's where we're defined. This is cosine theta. Now this is greater than 0 for theta is less than pi over 2 and greater than negative pi over 2. So if it's greater than 0, we can remove this absolute value sign. That's just equal to 2 cosine theta. So now that we have all of this, let's put it all together. So we get integral of u minus 1, square root, square root right here is 4 minus u squared of du. This equals 2. I'll just go and make sure that was the correct one. So we have u minus 1, 4 minus u squared du. So now we plug in u, which is 2 sine theta, and then du is 2 cosine theta d theta. So we put that in. This would equal to 2 sine theta minus 1. And then du is going to be, well, 2 cosine theta d theta. And now this square root 4 minus u squared, that's equal to this right here, which is 2 cosine theta. So now what we do here, I'll put this in bracket, this 2 will cancel with this one, and this cosine cancels with this cosine. So what we're left with is equals 2, just 2 sine theta minus 1 d theta. So now that we have this part, what this equals to, we can solve this integral. This one is just, well, integral of sine theta is just negative cosine theta. So negative cosine theta, and now this integral of 1 is just theta. And then we always have to add a constant. So that's the constant c. And now we have to get back to our x variable or our u variable. So let's write that here. So we got to get back to x. And to first do that, well, let's get back to u first. So we know that, well, 2 cosine theta is equal to square root, so always go back here, 2 cosine theta is equal to square root 4 minus u squared. It goes to 4 minus u squared we found, and then this 4 minus u squared is basically our original function. So that's what we just rearranged all of this to. Yeah, basically as shown here. So this is exactly the same thing, where u is just x plus 1. So going back to here, so this one is a rearrangement of the original one, which is square root 3 minus 2, 2x minus x squared. So this is just rearrangement of this, where u is, well, x plus 1. So we got this part, and now the theta, well, we know that u is equal to 2 sine theta, and well, basically u is equal to, well, x plus 1. So this whole thing equals x plus 1. Rearranges for sine, so sine theta is equal to x plus 1 divided by 2. And now we could just use the inverse. So theta is equal to inverse sine of, well, x plus 1 over 2. And now we could just plug these all inside. So we've plugged those in, actually not there, plug these inside here. So plug those in, we get finally, so we get the function here, x3 minus 2x minus x squared, dx is equal to negative of this 2 cosine theta, which is going to be negative of this right here, 3 minus 2x minus x squared, and then we subtract this theta, which is just inverse sine of x plus 1 over 2, and now this is just, well, plus the constant c. So there is our answer. And now here what I've done to illustrate this further is graphed out both this integrand, or this inside of this integral, and the integral itself, which is this. So as you can see right here, this blue is the integrand. So this one right here is, if you look at, it's the inside function right here. So that's this one right there. And now this red is the integral itself. So that is, well, this one right here. So that's the whole thing. That's the integral, is this. So as you can see, the integral is basically, well, I'll write this down, it's the anti-derivative. So if this is the antiderivative, the integrand itself is the derivative of it. Because remember, we're always looking for the opposite of the derivative. So this antiderivative, so this, if this is a derivative of this function, this means that, as you can see right here, as at basically x equals to -3, we get, well, -3, plugging inside the integrand. Yeah, plug it inside here, so we get -3 and then square root 3 plus 6, which is 3 times 2, positive, and then minus, well, 9. So this adds up to basically -3 over 0. So we go to, well, negative infinity, and that's where we're going here. And as you can see, this is the derivative, or the rate of change. So this one is going down. So yeah, we're going down a steep decline, because again, this is approaching infinity. And then, as you can see, as we're going back to here, this derivative is 0. at this flat line. So this flat line derivative is 0. Alright, equals 0, and that's at this point right here where it's the derivative. And then as it goes to 1, you have this steep incline, or this, and this is going to plus infinity. So basically at x equals to positive 1, we get 1 over 3 minus, well, 2 times 1 minus 1 squared. This just equals to 1 over 0. This goes plus infinity. So that's the derivative is going to infinity, and that's where this steep incline is, and it's not defined here, so we just draw a circle there. And there's an asymptote line here. So yeah, it's pretty messy here, but I just want to go over it. If you watch the video, it should be not too bad, but if you were to print this notes out, this would be a bit messy. Anyways, thanks for watching. Hopefully you learned from this pretty extensive example. And like always, you could download these exact notes in the link below, and stay tuned for another math easy solution.